So the goal of this second part, so we have two goals. First, upgrade the Sullivan model functor to operads. And second point, explain how to do rational homotopy computation with operads. Sorry. So I'm going with this first part, the Sullivan model functor for operads. So reminder. So I have this functor of piecewise linear differential forms from the opposite of the category of simplicial sets to the category of DG commutative algebras. This functor is not symmetric monoidal. It's only So the problem is to fix this flow in order to get something which works for operads. So the idea is to look at the adjoint functor. The adjoint of this functor. Take this functor G, so GA for DG commutative algebra, just the set of DG commutative algebra morphisms from A to the DG algebra piecewise linear forms on delta dot. And you see this one is actually symmetric monoidal. At least we have a G of A tensor B. This is equal to GA tensor cross GB times GB, because the tensor product is just the coproduct in the category of DG algebras. And if you take G of the ground ring, so Q, then you get a point, because the ground ring is the initial object in the category of DG algebras. So this functor G, this G is a monoidal functor, is symmetric monoidal in the strong sense. It's symmetric monoidal. And you have no difficulties. And as such, G induces a functor. I have to introduce some convention. So G from DG of C, so 1, 2, simplicial of 0, 1. So this is the category of operads in simplicial sets. In simplicial sets. And 0, 1 says that I'm restricting myself to operads which have the empty set in reality 0, and So P0 is the empty set, and P1 is the unit, so maybe I could write a star, is the 1-point set. Okay. Okay. And on this side, so this is the category of corporates. Hopf says that I'm considering corporates in commutative algebras. Okay, in DG commutative algebras. Okay, maybe. And 0, 1. So 0 says that such that C0 is 0 and C1 is K. Okay. So I use the name Hopf-Oprat to refer to the structures. DG, Hopf-DG oprat, DG co-oprat. So Hopf-DG co-oprats is a collection of DG commutative algebras together. So, okay, so to be explicit, so an object in this category, in this category, is a collection of DG algebras DG commutative algebras R is n such that A0 is so 0, A1 is K, with an action of a symmetric group on each term. And operatic composition coproducts. Sorry?
Cohomology of topological operad. This is an example of.
Yeah, exactly. Yeah. Operatic composition. Coproducts. So circle K, star goes from A m n minus 1, m plus n minus 1 to A m tensor A m. So now I can use this functor G to define the operatic upgrade of APL. Okay. This is just a proposition. This functor G and maybe I should make a comment about this convention. So I'm using that to fix difficulties with coproducts in co-multiplicative structures. I mean, you see, so these conditions ensure the existence of co-free objects in this category. If you don't put such connectedness conditions, you face difficulties because you get coproducts. So if you iterate, you get iterated coproducts landed in Cartesian products, and you face the usual difficulty that the Cartesian product doesn't commute with the tensor product. So in this case, so you see you have the rarity grading here implies that if you iterate coproducts, then you get nothing at some point. You get some rarity zero component at some point. Okay, so I have this functor. And I claim that this functor has a left adjoint. So a right adjoint. So because this is contravariant, I never know where's the right and the left adjoint. So it says the right adjoint. And I will take this right adjoint I have no here. A sharp. The idea is to take this right adjoint as an operatic replacement of a Sullivan functor. Okay. So the idea take this A sharp as an operatic replacement of APA. Okay, so you just know that this right adjoint exists. Okay, so you have to prove that this works actually. Okay, so for that you need to analyze this A sharp. So first I would like to describe, so give another proposition. What I can do easily is to describe the maps from going from some operads, some up operads to this A sharp. Okay, so we have a 1-to-1 correspondence between the morphisms of Hopf cooperads, DG cooperad morphisms, phi goes from C to A sharp of P. So C is any DG of cooperads and P is any operad in simplicial sets. And the collection of maps, the collection of DG algebra maps, morphisms, phi sharp R, going from CR to APLPR. So I'm now considering the plane Sullivan model of each space PR. Okay. Each PR in simplicial sets. And you need a condition you need a multiplicativity condition which satisfies, so I should say such that the diagram, the following diagram commutes for every operatic composition operation circle K. So what can you do? You can start with a model of C rather. You can start with Cm plus n minus 1. Take your product coproduct, you land in Cm tensor Cn. Then here you take the map phi sharp Mn plus n minus 1. The tangent of this map is APL of Pm plus n minus 1. So here you take phi sharp m tensor phi sharp n. So the tangent is APL Pm tensor APL Pn. Okay, and then you have the chain connecting this object. So first the QNF weak occurrence. So yeah. The QNF map. And here you take the image of the composition point of P under this functor APL. Okay? So you have to assume that this diagram commutes. Okay? So this is a formal consequence of the adjunction relation. Okay? So the point is that to construct maps in the homotopy category, you have to work with this model A sharp, but this one gives some kind of connection with the plane, the concrete Sullivan model. Okay. The consequence of this proposition is that you have a map, the corollary. So we consider the DG commutative heteromorphisms. So, or rather, I should say you have comparison maps. I'm denoting them by K. Here, and this go from A sharp of PR and to APL of PR. Okay, so maybe I'm wrong here. I should say so. This A sharp of PR doesn't exist. So here I'm taking the half component of this operad. Okay. Okay. So for every R. So these are the morphisms that corresponds to the identity of A sharp PR. Such that. Okay. Okay, the identity of PR. So the main statement says that these morphisms are weak occurrences of DG commutative algebras, at least under some assumptions. So if each PR satisfies the standard assumptions associated with the Sullivan model, if the cohomology of each PR is a finitely generated module in every degree star, is degree-wise finitely generated module. It's finitely generated as a K module. Is finitely generated as a K module, as a Q module in each degree star. Then this map is a weak occurrence. I forget an assumption. And P is covariant as an operad in simplicial sets. So. Then, so I'm not going to explain this assumption for the moment. Then this map is a weak equivalence.
Except to admit that it's quite restrictive.
No, every operad has a covariant replacement. So, yeah. No.
Okay.
Okay. Then this map chi has a covariant. Then this chi is a weak equivalence.
But then having the two conditions might be restrictive. If you take a covariant replacement or an operad.
Then you don't change the cohomology.
No, that's
Oh,
right.
okay, sorry. It's a
So- so- yeah.
It's already a derived functor. So your lower sharp is already, in some sense, you could replace it by its Quillen derived functor, and then this would.
Yeah, exactly. So in any case, this A lower sharp, I'm going to take the derived.
Say the same thing again.
Yeah. In any case, I'm going to take this derived functor of A sharp. So I already have APL. So I forgot to mention that I'm taking the derived functor of this APL. But on the category of simplicial set, you don't see that because every simplicial set is covariant.
Yes.
Configurations are just injective maps, and which map is obviously injection. So, but in the operatic case, you see already this assumption appear at this point. Okay. Then this chi is a weak equivalence of DG. Maybe I could give a sketch of a proof. So actually, yes. So actually, if I have an analogous statement in the simplicial setting, so I have two parallel statements. I have this one in the differential grade setting. Okay. So I have this A sharp, which is the functor from DG, from DG of corporates. Oops, sorry, that's the other way around. From simplicial operas to DG of corporates. And I have an analogous functor so this is the upgrade of APL. And I have an analogous functor which lands in the category of cosimplicial of corporates. And this one is an upgrade of the obvious Q to K. Okay, the functor from simplicial sets to cosimplicial commutative algebras. Okay, and the points that so technically I prove this statement at the cosimplicial level first, and then I use that this category are Quillen equivalent actually. Okay, you have yeah. So it's yeah. Okay, so the idea is first proof. So proof one. So the plan is to prove one first, and then use an operatic upgrade. Upgrading of the Dolcan equivalence. So to get that this category is Quillen equivalent to this one, and to get this case 2 from 1. So I'm going to give to outline this proof, the proof of 1, in the simplicial setting. So the co-simplicial setting. So the first step is to observe that this functor A sharp is the simplicial extension of a functor from operad in sets to co-operads in plane commutative algebras. Okay. So this means that this means that for a simplicial operad, the component in dimension n of this co-simplicial of co-operad is just given by the application of this functor on set theoretic operad to the nth component of P. Simplicial dimension. For every dimension n. The second point that is to address the case of free operads. So for free operads, we have that A sharp of a free operad on some generated by some symmetric sequence M. By adjunction, this is just the co-free co-operads on A M. And the idea is just to get the QNF equivalence to obtain this case. So this is obvious by adjunction. The idea is to use to get this case. The first step is the idea is to use the co-triple resolution. I mean, if you start with any operad P, in the case of simplicial sets, you form the object which is it's a simplicial object. Actually, it's bisimplicial. Okay. So, and in dimension S, this is just given by the application of S plus 1 times the free operads to P. Okay. Called application of the free operad functor. And the face maps in these simplicial objects are just given by the monad structure maps of the free operad functor. Okay. So now the point, this is an instance actually of a covariant resolution of P in general. Okay, so these are so this is the diagonal object associated to this operad. Is a covariant is an instance, at least if P is yeah, maybe there are some points. So you have to assume that P is covariant of the symmetric sequence, but this doesn't matter. Covariant replacement of P.
Like tensor with particles.
Okay, yeah, otherwise you can tensor with particles.
Say product with
Maybe I could assume that here this is an extended free object where you take this tensor product too. Okay. Yeah, okay. Covariant replacement of P, at least if P is sigma covariant. And to conclude the proof, the idea is to use the Wallenberg-Zilber equivalence. Oops. Which says that if you take so if you apply this functor A sharp to this diagonal object, okay, oops, so then so diagonal you can put where you want, outside or inside. And Wallenberg-Zilber equivalence says that the diagonal of this bicosimplicial module is equivalent to a tot object where you separate the dimensions. Okay, you assume that one is the horizontal dimension, the other one is the vertical dimension.
Yeah.
And then you just use what?
Why do you call the thing on the right diag? Because now you have a cosimplicial thing.
No, it's
Because
no,
A
it's
sharp is-
bicosimplicial because this is contravariant.
But if of the other thing, so
Ah.
what's the diag on the left?
Yeah.
If it
So,
was
sorry. So it's this one is bisimplicial, and you apply this A sharp, which is a functor on operad in sets,
Yes.
and you get a bicosimplicial object.
Yes. Oh, it reverses both directions.
Yeah, both
Yes.
directions.
Oh yeah, of course.
Okay.
Sure.
So here you crucially
Yeah,
use
that's right.
this observation one.
Yeah.
Okay. So this is the Wallenberg-Zilber equivalence, and then you can use a spectral sequence argument and the case of free operads to conclude. Okay, so I mean, if you fix that dimension, this horizontal dimension, then you are reduced to the case of a free operad, because this is an S+1 fold free operad. To conclude. Okay. So now I can use this to get a model, okay, for operads, and so to get a model and to define a rationalization functor on operads. Oh, maybe I forgot. Maybe before I would like to say something. So, for instance, if I maybe I could explain the example of little disks. Okay. If you consider the case of a little n disk operad, P. You can take the singular So to get a model of this operad in simplicial set, you can take the singular complex of this operad Dn. Okay, but actually in this, so it's actually it follows from from Koncevich's formality theorem. And also you can use this theorem as you have to use also some improvement by Lambrechts and Wolich. Implies that we have a chain chain connecting the cohomology of little n disk so chain of equivalencies of DG of DG cooperads. So, which connects the cohomology on this model. Okay, the periodic upgrade of Dn. Okay, so actually they use the Fulton-McPherson operad rather than. So maybe I should write the Fulton-McPherson model.
Which by the previous comment is the same thing.
Yeah.
Then, because
yeah.
you take a cofinite resolution and then apply Sharp.
Yeah. Okay. So here you have to. So here it's okay. Maybe here you have to take a covariant resolution of a singular. So something big in any case. Okay. Because you have to apply the singular functor, which is not covariant. So you have to perform a covariant replacement, and so on. So I should say, so these authors, they have defined this kind of collection of maps which satisfy the multiplicativity condition of the previous proposition. So you see the proposition implies that these maps are equivalent to such a chain, okay, of operad morphisms. And so this says that the operad of little disk, okay, is formal in the sense of this model. Okay, so most statements that the operad of little disk is formal as an operad in chain complexes, but you actually have more. The formality result holds also for the DG commutative algebra structure of a model. You have a chain which is both, this chain of equivalencies is both compatible with the DG commutative algebra structures, which encode the topology, and with the corporate structures, which reflect the structure of little disk. Okay, so it's a kind of improved formality statement. So actually, there is a point for that we know only that this is true for R, at least.
Can I make a comment or?
Yeah.
So I think I understand what's going on there when you're taking a resolution of the singular complex
yeah.
of the Fulton-McPherson. So let's take, you've got like a sphere for n equals 2 in the Fulton-McPherson sphere of
yeah.
operations, and then you can compose them. So now inside, so you have some copies inside FM3 of FMN3 tri operations of products of two spheres. And so now when you take the singular complex, that's not the product of the singular complexes of the two spheres. So in taking the resolution, in throwing in higher simplices and then taking a diagonal, where you have free operads, you're effectively putting all the homotopies you need that are missing
Yeah.
so that you can, as it were, slide over two products of
Mm,
simplices in those two spheres, and thus retrieve covariancy.
Yeah.
And that's
But
somehow
in any case, so it's a big
it's all
concept.
automatic, I
Yeah.
understand.
Yeah.
But
so the point,
yeah.
what we would like to use is this, the
Yeah.
cohomology, which is
Yeah.
simpler. So this is the Gershnaber operad, actually.
But by taking that resolution, you
Coprad.
just like automatically
Yeah.
put in all
Yeah.
homotopies you could ever
Yeah,
get.
yeah, exactly. So that's,
Yeah.
okay, so this is the Gershnaber operad. Okay. So we can take this as a model for Dn. So in the case of DG operad algebras, at least if you take this. So I know how to get a formality in one direction. So it's possible to get a formality over Q if you forget about one part of a structure. I mean, these objects are formal over Q as spaces or as operads. But I do not know how to reduce, how to have such a statement over Q if I mix all structures together. So I'm conjecturing that this is true about Q. But I don't have the structure results yet to get such a statement.
Is that because Koncevich's formulas are over the real numbers?
Yeah, exactly. Yeah. And the conjecture is that if you have formality over some field K, of some characteristic zero field, for hop DG op, for this DG op, for this op DG coprad model, then you have formality over Q. So that the point that so this is true in the case of if you forget about operad structure, then you have such a statement for spaces, which is this is in Sullivan's paper. If a space is formal over R, then it is formal over Q. Okay, but for that is using the minimal model, and I don't have minimal model in this setting so far.
You don't?
Okay.
You kind of do, don't you?
So for the moment, I don't have minimal model.
Yeah.
So it's I don't know how to get a model which is minimal, which is both an operad, which is minimal. So it's a free model. In the so an operad which is free as an operad, which is quasi-free,
So
but which is
it's what did he call them? Hirsch extensions. A minimal
Yeah.
model is an iteration of Hirsch extensions.
And the problem is that I have to do that. And with I need some Hirsch extensions which are with a corporate structure. It's some, okay. So maybe I'm going to explain how to do this homotopy computation. Okay. So I need again to define a model. So again, M. So there's operads. So simplicial operads. DG hop operads are cofrequently generated model categories. So this means that in both cases you have the structures you need to do homotopy computations. And again, I would like to summarize the structures in a table. So I have on the left-hand side simplicial operads. On the right-hand side, DG hop corpus. So the equivalencies in both cases are created arity-wise in the base category. Okay, so in that case, this means the equivalencies of operads in simplicial sets are the operad morphisms, which are equivalencies of simplicial sets in every arity. In this case, these are morphisms of hop DG corporads, which induces a an iso-incohomology in each arity. So what are the generating, so say I, the generating configurations? So in that case, what I take are the morphisms of three operads. So from F, K, cross G R with G R F of the following form. So I runs over the generating configurations of the category of simplicial sets. So these are the maps from the boundary of delta n to delta n. Okay. And GR is a symmetric sequence, the sigma object, such that GR of n, so this is sigma R if R equals n of empty set otherwise. Okay, so it's a free sigma object with one generator in arity R. So this means in that case, when you want to deal with cell objects, so cell complexes, you are using some objects which are free with respect to the operatic part of the structure. Okay. So in that case, I need objects which are free with respect to the commutative algebra part of a structure. So these are symmetric DG algebra morphisms. SI from SC to SD. And these are the morphisms which are associated to co-operad morphisms, I from C to D. And I will consider only co-operad injections to injective morphisms of co-operads. From C to D, such that, and you put some smallness assumptions on the operad. So each Cn and C and D are globally finite dimensional. So this means that Cn is 0. And the same for Dn when the arity is large enough. And otherwise, the chain complex, each the non-zero components are bounded. Okay. And the components that are non-trivial are finitely generated. The cube of the different ways. Maybe I need to make a remark about the construction of this co-operad morphism. I mean here that if C is a co-operad, and what I consider is the collection SC consisting of the symmetric algebras on the components of C. Okay. And so this is a collection of DG commutative algebras, and the point that this collection inherits a coprod structure. Okay, this collection inherits coproducts. And forms a Hopf DG coprod. So the point that so I define Hopf DG coprods as coprods in commutative algebras, but you can do the definition the other way around. Say that a Hopf DG coprod is a commutative algebra in the category of coprods. Okay, now I'm just taking 3 commutative algebras in this base symmetric monodal category, in the category of DG coprods. Okay, so I'm just remember this just means that I'm performing the symmetric algebra construction reality-wise. Okay, so I have configurations, and I can take the same definition for J. Okay, just replace. So to get the generating acyclic configuration, I just replace the word. I just put weak equivalences here. I'm just considering the generating acyclic configurations of simplicial sets, and here I'm just considering injective morphisms of coprods, which induces an isone cohomology. So with that, I can define fibrations, okay, which are characterized by the left lifting property with respect to J. Left lifting property with respect to J. Okay. So in this case, in the case of simplicial operads, this is the same as the reality-wise Kant fibrations. I mean, in this case, the fibrations of operads in simplicial sets are just the operad morphisms which form a Kant fibration in each reality. In this case, there is something. Okay, but I have no better characterization. Okay, I just say I can use some kind of co-free coprod constructions to realize such fibrations. Okay. So now the proposition is that the functors so G induced by the adjoint of the Sullivan model functor from DG Hopf coprods to simplicial operads. And the right adjoint, A sharp. So these functors form a Cullen pair. So they have induced adjoint functors at the level of homotopy categories. Okay. So So now what I would like to do is to start. So I start with the covariant operad in simplicial sets. Okay. So I can apply the functor A sharp. Okay. So in that case I have to take care that I have to take. So not all objects are covariant in this category. Okay, so when I apply A sharp, I have to restrict myself to covariant objects. If an operad is not covariant, then I have to perform a covariant resolution of this object. So I take A sharp of P. And then I go back to topological spaces by using the adjoint of this functor. So I define P hat by this composite construction. Okay? So the theorem is if each cohomology of PR is degree-wise finitely generated module, then this P hat comes from an adjunction construction. So this means that you have an operad morphism. So this is from P to P hat, and so this is an operad morphism. Which is a rationalization of space in Sullivan sense, arity-wise. So rationalization in the sense of Sullivan. Okay, so I get another operad, P hat, which is connected to P by a morphism which induces the rationalization at the level of homotopy groups. Okay, so this is a consequence of a previous statement and of the fact that in my definition, you see that the cells which are used to build the cofibrillations are actually cofibrillations in the category of DG commutative algebras. Okay. So if you apply this functor, this derived functor in the category of DG of Hopf DG cooperads, then it agrees with LG, the derived functor of the adjoint of the Sullivan model functor in each arity. Okay. Okay. So we have a rationalization functor which works for, at least for all operads satisfying some mild condition. Maybe so rationalization here means that it agrees with Sullivan, and again, so you have to add some conditions, maybe to assume that each space PR is nilpotent to get the statement about the effect on homotopy groups, but in any case. Okay. And so the point is that I don't know how to construct such a functor for all operads without using this adjunction. And maybe it's possible by using fundamental, the CAN group construction, GK, but I don't know if it is symmetric model. It's not clear. So, yeah. So this works actually. Okay. Okay. Maybe I would like to see how this applies to the case of D2. Okay. So I can use this classifying space of a parenthesized braid operad, which I used last week. Okay, and I said so I replace the groups of pure braids by the group weight of parenthesized sprites to get an operator structure. And I have one at the classifying space level. Okay. And then, okay, I can take, so this operad B, PAB. So last week I used a Maltsev completion of this PAB. So now I can use this, the derived functor of G, and the derived functor of A sharp, which I apply to this operad. Okay, D2. And I can also apply this composite construction to this operad. Okay, and you can, so this map, so it's, yeah. And you can analyze, so these maps are, so you have operad morphisms, so this follows from the functoriality of a construction. The construction can be made functorial, okay, because you have functorial cofibrant and fibrant resolutions. And so, and you can check that these maps, which are operad morphisms, induces ISO on homotopy groups, because in all cases what you get are rationalization of purebred groups, or Maltsev completions of purebred groups. So you still get a construction which works for all operads, which gives the same answer as this classifying space of a Maltsev completion construction. Okay. So now how to compute this object. Okay. So for that I can actually use this. So I would like to examine the application of this construction. So I need a reminder. So to do that, so I would like to compute this. Actually, so what I would like is to understand this object rather. So for that I can use, or rather I would like to have a cofibrant replacement of this object. So for that I'm going to use the Drinfeld-Kono Lie, so the Lie algebras of infinitesimal braids. So in the first part of my talks I explained that if I take the Chevalier-Eilenberg cochain complex of PR, this Lie algebra of infinitesimal braid, then what I get is something which is equivalent to the cohomology of the conversion space of R points in the plane. And so this is the same thing as the two-fold Gershner-Haber opera, the second Gershner-Haber opera, or the dualized corpora. And actually, you have a corpora structure on this side which reflects this corpora structure here. Actually, this is a cofactorant resolution, so I have to define the corpora structure. So for that, I'm going to use the chord diagram pictures of this Lie algebra. So L, so PR is the Lie algebra generated by elements denoted by Tij, which are associated to pairs. Divided by some relations. Okay. So in the literature about Vassiliev invariance, Tij is represented by a chord diagram on R strands the chord joining the ith and the jth strand. So for instance, so here is the picture. And so the relations, the infinitesimal braid relations, have an interpretation in terms of chord diagrams too. The collection of these three algebras form an operad. The category of Lie algebras. So this means you have operatic composition maps. So you have to specify a tensor operation on the category of Lie algebras, and this tensor operation is the addition of Lie algebras. So and these operations are just some kind of cabling operations. I mean, if I start with such a chord diagram here, plus 0. So what I'm just going to do is to insert n parallel strands on this on the kth strand here. Okay, so in that case I just get the following result. I k until k plus n minus 1. So here this is, I have to perform some shift, j plus n minus 1. And, oops, m plus n minus 1. Okay, I just insert and the vertical strands at the kth position. So in the case where k is I, for instance, then I do the same thing. I insert n strands on this position. Okay. But now, you see, so this is j plus n minus 1. So I have to say to which strand here I have to attach this chord in the outcome. The idea is just to sum over all attachments on the inserted strands. Just sum over all positions L. So this is for L from k to k plus n minus 1. Okay. And you have a symmetric picture if k is equal to L. Okay. And you have also composition maps of this form. And thus this map is just given by the insertion of such a chord diagram on a chord diagram with only vertical strands. I mean, you just insert this chord diagram at position k. Okay. So you have such operatic composition maps at the Lie algebra level. As a consequence, this object, you get cooperatic composition coproducts. Okay? Right. Of DG corporate structure. And you can check that this cosine duality maps preserve this structure. Okay. In fact, claim maps kappa, the cosine duality maps define a corporal morphism. So this operads forms a covariant resolution of this operad.
Cofibrant in what sense?
Sorry?
Cofibrant is an operad or just cofibrant?
In the DG of
You just mean the cofibrant differential graded commutative algebras.
So it's a covariant object in the category of DG cooperads.
Oh, it's actually cofibrant even operatically.
No, it's not operatically. Covariant is with respect to the commutative algebra structure.
In the cooperant direction it would just be
Yeah,
like
in the-
cofibrant is nothing.
So in the cooperative directions, you have to deal with fibrant structures.
That's it, there's a hard one.
Okay?
Yeah, got it.
Okay.
Yeah.
Okay.
Why do you call that dual map?
Because-
Duality map.
So this has the map which, yeah, okay, cosine duality. These are the maps which comes from the fact that each of these algebras is cosine as an algebra. Okay. Okay. And so the consequence is that you can use this object to compute the rationalization, and you get the same picture as in the Sullivan case. So you get that if you take this object, LG, so this is G applied to this model. You get the collection P hat tensor omega P. Okay. So you just perform the construction of a previous part RET-wise, and you get a model for the rationalization. Okay. And what you get here is something which is equivalent to the classifying space on the same object as in the previous part, the group-like elements in the enveloping algebra on P, where now you take the whole collections of this object to get an opera. Okay. So when I don't park the P, this means that I consider the collection of all these objects, which is, so this is an operad in group weights. Okay. And this is actually the operad of chord diagrams. This is also called the operad of chord diagrams. Chord diagram operad. Okay. So actually, you see from this statement that, yeah, maybe.
Sorry, where did your last statement come from? Is it just additional information, or can I see that from what you said before?
Sorry?
The last statement, is that additional information, or can you see that from before, that this is the algebra, that this is the E of the operator of chord diagram?
Yeah, in fact, you have, so it's another approach. Yeah, you have two, so you see you have this object, okay?
Yeah.
So this is just a formal consequence. So this is just, yeah, this is just a formal computation, okay?
Right.
And this, so this is for this kind of object, you get a classifying space. So it's a general statement. And you can see that this works when the object, so it is a statement for all the algebras. And if you start an operad in the category of Lie algebras, then you get such a weak equivalence for the category of operads, I mean. The category of operads, in simplicial operads. What I would like to say now is that so I have said that this is a model for D2. Okay, this gives a model for D2 in the category of DG operads.
This was only in the real case.
Yeah, only the real case. Yeah, exactly. Yeah. Okay, and so that way you get that this object over the real, it's weak equivalent to the classifying space of PAB, at least over R. Okay, you have an weak equivalence of operads. Okay, because this is not the model for the rationalization. Okay, so the weak equivalence that you get on the model, you get it at on the simplicial operad level. Okay, and then from that you can apply the fundamental groupoid constructions to get that you have a groupoid the equivalences of group operads and groupoids from this object to this one. Okay, so you can retrieve the existence of associators by applying. So these maps here, the operad morphisms here, are just Grunfeld associators. Okay. Applying fundamental groupoid.
So this is like the hardest proof.
Yeah.
It's an association.
Sorry, can you say again why you a priori that these two things are weak equivalent?
Because these are two models. So because you know, so this is the same as GSG A sharp of D2. Okay. Yeah, because okay, so this is my first argument, and you have the formality. The improved formality says that this is equivalent to this one as no operad. Okay. Okay.
But
So
formality uses associated.
no. So yeah, you have two. Actually, I would like to say that you have two equivalent proofs. You have a Kontsevich proof, which is you establish the existence of such equivalences directly. Okay, and now you use this functor. You apply fundamental groupoids, and you get the existence of associators.
Oh.
And you can go the other way around.
Oh, so you didn't use formality to.
And you have, okay, if you have the existence of a Grunfeld associator, for instance, the Kijnik-Zamoyski. Sorry?
You do use
He
formality.
is using formality to get the existence of associator.
Yes.
Yeah, that's right.
Yeah.
You can use formality to get the existence of associator.
You could use
Or the other way around, you can use the existence. Okay. Sorry?
Formality uses Kontsevich integral.
Yeah, exactly.
Yeah, but
So you have also a more direct way to go from here. You have also a direct way to go from here to here. Actually, you can use some explicit integration process to directly get these results. So this is what is done by Severa and Vilvarer and Alexeyev Torosian.
Yes.
Okay.
but all proofs are transcendental.
No,
So-
but they use another associator.
Yeah, there's another associator.
So
They use Kontsevich associator. So Kontsevich associator is formally equivalent to that, and this is a kind of decomposition of something enlarged. I enlarge the Severa Vilvarer proof This implies the existence of associators. Okay, so you can use some kind of parallel transport construction to get this result directly. And the other way around, if you know that associator exists, if you have the existence of an associator, then you can use the classifying space construction to get an equivalence between this object and this one. And by going through this zigzag, you get the formality.
Therefore, you have full.
So just to clarify, is it true that then there's no non-transcendental proof of this?
Sorry?
That all the different ways you outlined of proving this go through are transcendental?
Yeah, exactly.
Is that correct?
Yeah, exactly, that's correct. Yeah. You need rational or complex coefficients, and then after that you have some kind of reduction, which is if you have, so in that case...
So you can't prove the existence of a rational associate.
Yeah.
It's this old problem about mixing the minimal models.
Exactly.
Yeah, and the coproduct.
Yeah.
So what do you do if n is not equal to 2?
If n is not equal to 2,
You ask constant?
then you have the same thing, but you have not the last part of the picture. You have not this...
Of course.
This part. This is still okay. You can define an n-dimensional version.
And this is this is cofibrant.
And this is cofibrant again. Okay.
But
And what you don't have is this. Okay. So you still have this, but it's not a classifying space. It's a more general KPN's construction.
so,
Yeah,
so
if you start
why is it not? You said it for any algebra. Yeah.
for any dimension n,
Oh, you mean?
you can define such a thing. Okay. At least over R. Okay. Then I don't know if this is true over Q.
You just said that from the line to the one you just tried out, it was completely general. Take any Lie algebra and then you get
But
No, from here to the next one.
Lie means concentrated in so this is for any Lie algebra concentrated in degree 0. Okay, now I'm considering graded Lie algebra, so I can't
if you
fix this
shift,
point.
it's very. You should just shift.
I don't get a classifying space. I don't get something which has only a pi 1. Okay,
Yeah,
it's
ultimately it's because the operad is not an operad of k pi 1.
exactly.
Yeah.
Exactly. Okay. So, but I can still do that. So this Pn just means that the generators now have degree n minus 1 or n minus 2 maybe. Something like that. N minus 2,
So
I
you
should say.
don't prove the formality of deal.
No, No, I'm
this
using-
way.
no, I'm using the formality, that's the point.
Can I?
Yeah.
So I want to summarize what I saw as the two key kind of machines that you incorporated
Yeah.
into the proof. One was that it looks like at least you quoted or used some result that you have some closed model categories. Although
Yeah.
I'm not sure how heavily you really used that in this part.
Mm.
But that's a heavily,
So I use that to
that's
define this
heavily-
LG. Yeah.
because that's heavily transfinite. I mean, at that point you're using
Yeah.
the actual
So I'm using
choice
maybe this resistance of
out
LG.
to forever. Yeah, it's a very kind of
Yeah.
like roundabout way of trying to understand.
No,
an
the LG,
explicit
I need
homotopy
I need
equivalence.
the model
Yeah.
structure to get that this functor preserves just
Yes.
weak occurrences. Yeah,
in general.
in general,
Yeah.
yeah.
So that was one thing that you're using,
Yeah.
which is a kind of big machine.
Yeah.
And the other not so big machine but beautiful idea is the co-simplicial resolution.
Mm.
That was somehow that's the key step in the construction of the sharp functor,
Yeah.
and thus in verification of its
Yeah.
properties.
Yeah.
So
Mm.
you basically are seeing that there's this clever way of putting all possible homotopies you'll ever need in a completely clear
Yeah.
way.
Okay.
Is that correct? Am I
Yeah,
understanding what you've done?
so the point that the co-simplicial resolution, that you can, the crucial points were in Berzilberg, you have to control things.
Yeah. Well, there's that too.
Yeah. Okay, maybe I will just, to conclude, explain how quickly to use these resolutions to compute mapping spaces and homotopy automorphism spaces. So maybe I'm not going to use the model in that case, not really. So what I would like to do is to compute operand maps. Oops. Oops, it's almost over. Yes. From the Grothendieck, so from dm to dn. So I will just say in a few words how to do that. And the idea is just this. On the left-hand side, you take this quadruple resolution actually. Okay, I can do that in Decatur spaces. And on the right-hand side, I actually use this construction, this object here. Okay? And so I get this object. Okay? So the plan is to compute the connected components of this space to get the homotopy classes of maps from dm to dn. So, okay, and so here I can take the g of the comma g2. Okay, in any case, so yeah. Okay, and so you have two directions. I mean, you have the operatic direction, which is resolved here, and the algebraic direction, which is resolved here. Okay, and so you have two directions of spectral sequences, and you have to choose which one you apply the first. So topologists would probably say that this one is the k-pi 1. So we know how to compute maps towards the k-pi 1. So I can just fix the result here and take a spectral sequence with respect to this dimension toward this object which is already resolved. But I don't know how to do that. And so the idea is to compute a spectral sequence which takes this first and this replaced by a symmetrical algebra. So you forget the differential. Okay. And it turns out, so in the case in m equals n equals 2, if you look at the E2 term of this spectral sequence, so here I'm crucially using that D2 is Kosul as an operad to reduce this computation to something which is identical to the equation for GRT. Okay, you get the same thing as GRT. And this is really because D2 is Kosul as an operad. So on one side I'm using that D2 is Kosul as an algebra, and on the other side I'm using that D2 is Kosul as an operad. Okay. And so you, at least in degree 0. So this is 0 in degree. And this implies that the spectral sequences collapses to GT at E2 at this stem already. So.
Did you get the pentagon only, or do you
yeah, what you get, you see that the hexagons are equivalent to some kind of equivalence condition, and the pentagon is encoded by the differential D1. So you have some. So you have maps of operads, so you can reduce these maps to maps of symmetric sequences. And the hexagon corresponds to a symmetry condition. And the pentagon are equations given by D1. Okay? So that's the point. Yeah.
So what do you say about the higher homotopy? So you saying anything about that?
Yeah, there is nothing. There is nothing. So this is 0. This is 0 in degree larger than 0. Okay. So this is something that you can get by using by resolving first on the right-hand side. Okay. So also to compare with Fresse. So this is a kind of deformation complex.
Yeah.
But here you see so in my case I'm removing, so I'm dealing with maps which incorporate both an operad structure and a commutative algebra structure. And actually this reduces the complex. So in Wilvarer's computation is dealing with the deformation complex where it forgets about the algebra part of the structure, actually. And this makes the complex bigger because you don't kill this symmetric algebra.
So you're saying that in homotopy theory we have to take a cofibrant resolution the first guy and a fibrant resolution the second guy.
Yeah.
And if in many special cases
Yeah.
one only has to do one of those, but in
Yeah.
this case you have to do both,
Yeah.
and then you happen to use exactly everything that's available to do
Yeah,
those two resolutions.
Yeah. Exactly. Yeah. And using that both, so you have a nice resolution in both directions actually. Yeah. So yeah, and I have a spectral sequence that generates at this level. So then I conjecture that this is also the case for M and N higher than 2 because of the formality, but it's still a conjecture actually.
So when you said, so on the left you use the Kosul to give a cofibrant model.
Yeah.
Is that what your point? Okay. Good.
Okay, thank you very much.
Thank you.